One of the most important topics in machine learning are gradients because they are used in a technique called gradient descent, which is used to train almost all of the machine learning models out there. So naturally, we first have to understand what gradients are. In machine learning, you are typically given a data set, and I've just written a very simple example here where we only have a single feature and a target value y, and this can be anything. For example, if we were to plot this data set, maybe we would get something like this, where the feature is the living area of a house and the target is the price of the house. And as you can see, the more living area you have, the higher the price. And from this data, we can see that there's a line that describes this data very well. And we denote this line as the target function. We just say, well, it's probably a line that defines this data. And that line is defined as m times x plus c, where m is the slope, c is the intercept. And then there's some Gaussian noise. Otherwise, all the data points would be on this line, but we can see that there's some noise on top of the line. So what we can do now is we can define our own model and say that our model has two parameters, theta 0 and theta 1. And we define our model as theta 0 times x plus theta 1. And our goal is to iteratively tune theta 0 and theta 1 such that theta 0 is equal to or close to the true value of m, and theta 1 is close to the true value of c. Because once we have these, we can use our learned model f to essentially query it on data we've never seen before. Because we actually don't have access to this target function, we just assume that it's probably a line, so it's okay if we choose a model that also depicts a line, but we don't have access to this. But if we had our own learned model, well, we could use that on new and unseen data. So now the question is, how do you find the right theta 0 and theta 1? And the answer to that is we use gradients. So what we do is we first initialize theta 0 and theta 1 randomly, and then we measure the performance of theta 0 and theta 1 using a loss function. So the loss function is another very important concept in machine learning, and there are different kinds of loss functions out there measuring different things. But in general, a loss function is there to measure the performance of your current set of parameters on your data set. And in my opinion, the most straightforward error function out there is the so-called mean squared error, where you simply take the output of your function, which I've denoted as y hat, and you measure the difference between your prediction and the actual target value, and then you square the whole thing. And squaring it is okay because first you get rid of the minus sign, that's always a bonus. Also, it's a linear operation, so the relative distances still remain the same. And also you make your loss function convex if your model itself is a linear function. And just as a side note here, what is a convex function? Imagine your function looks like this, then it is convex if you draw a straight line through it and it intercepts your function only in 2 points. For example, this function right here is not convex because this line goes through 3 points. So this is not convex, whereas this one is convex. And that's just a little side note. You can actually prove that a function is convex if the Hessian of that function is positive semi-definite for all inputs of f. And we won't cover that here, maybe some other time, because that's actually a great question for an exam. But for now, we will skip this part. So now we can put our current set of parameters in a vector notation like this, and we want to change our set of parameters in such a way such that the new thetas, the new pair of parameters, if we were to put them in the loss function, then the output of the loss function is smaller than our previous set of parameters. And that's what we want to do. That's the iteratively tuning part. And the question is now, well, what is this magic vector that we add or subtract from our current set of parameters in order to get a better set of parameters? And the answer to that is that this is the gradient of the loss function. So in order to understand a gradient, we first have to brush up on derivatives. So I've got this function here, 2a squared plus 4. And if you were to plot it, you would get perhaps something like this. And the derivative of this function is 4a. And the derivative is defined as the slope of the tangent line. So if you draw the tangent line here at some point, then the slope of this line is the derivative. The derivative is the instantaneous rate of change of a function at a particular point. And another way to define the derivative is like this, where you have the limit where h tends towards 0, and it is defined as f of x plus h, where h is a little nudge in some direction, minus f of x, divided by the size of your little nudge. So in other words, it's the delta in y divided by the delta in x, and that will be this part right here. That's just another way to write the derivative. But now what if we had a function like this? So f of ab is equal to 2a squared plus 4b cubed. Now in this case, you couldn't compute the derivative as you did before, because you can only compute the derivative with respect to a single variable. In this example, you only had a single variable, so that was kind of implied. But in this case, it's not implied anymore, and the only thing you can do is to compute a partial derivative with respect to a single variable. For example, if you were to take the partial derivative of this function with respect to a, then b becomes a constant, and the partial derivative is 4a. And if you take the partial derivative with respect to b, then a is the constant, and you're left with 12b squared. And the gradient is a vector which contains all of those partial derivatives. So it's a partial of f with respect to a and with respect to b. So in this example, that's 4a and 12b squared. And that's the gradient. The gradient is a vector which contains all of these partial derivatives. It's kind of like the full derivative of a function. That's how I like to think about it. And its direction is kind of like the average rate of change of the function. Because the gradient is a vector, it's got all those vector properties, like it points in a certain direction and it has a magnitude. And it's got one more special property, which is that it points in the direction of steepest ascent. And as you can see here, I've added a little asterisk because yes, it is a vector, but it's also a vector function because it depends on the input a and b. As you can see here, it's not a constant vector. It always depends on the input a and b. But now let's have a look at this special property that it points in the direction of steepest descent. And the question is, why does it point in the direction of steepest descent? So every function creates a sort of landscape, and you will see an example of this somewhere on the screen right now. And I would like you to imagine that you're standing somewhere on this landscape, and your goal is to get to the summit as quickly as you can. And let's also say that you are blindfolded and you can only take a single step in any direction and feel the steepness of the ground if you were to move in that direction. So let's say you're somewhere here and you want to go in this direction V. Now the question is, how steep is it if you were to go in this direction? And you can compute this by using the directional derivative. So the directional derivative is computed like this, where you have your gradient and you take the dot product with it and the direction you want to go in. And that in turn is defined as the magnitude of your gradient times the magnitude of your vector times the cosine of the angle between them. So in this case, that's theta. And since V is a unit vector, its magnitude is 1, so all you're left with is the magnitude of your gradient times the cosine of the angle between those two vectors. And that can be any number. For example, that's 1.74, and this number stands for the rate of change, so it's a rate of change of 1.74 units per unit traveled. So moving towards this vector V leads to a rate of change of 1.74, but that may not be the one vector which maximizes the steepness. It may not be the vector that leads to the greatest rate of change. There might be another step you can take somewhere from this position that gets you to the top quicker than this V. And the question now is, which vector maximizes this part? And the answer to that is, well, it must be the vector whose angle between the vector and the gradient is 0, because if the angle is 0, then the cosine function reaches its maximum of 1. So what we can see here, if we were to draw it again, the vector whose angle with it and the gradient is 0 is the one that maximizes this function. So for this vector u, we have again the same formula. So it's the magnitude of your gradient times the magnitude of u times the cosine of the angle between them. And u is a unit vector, so its magnitude is 1, and theta in this case is 0 because it points in the same direction. Then you're left with the magnitude of your gradient times cosine of 0, which is 1, and the final result is the magnitude of the gradient. And this also happens to be the maximum rate of change you can achieve. So what we found out is that the vector u points in the direction of steepest descent, the gradient points in the direction of u, therefore the gradient also points in the direction of steepest descent. So to summarize, we were looking for a vector which maximizes this part because that leads us to the greatest rate of change. We found out that there's only one vector that does that, and it must be the one whose angle with it and the gradient is 0, because in that case this cosine function reaches its maximum. And if the angle is 0, then it means that that vector points in the same direction as the gradient. And because this vector definitely points in the direction of steepest descent, because it must, since the cosine of 0 is 1, that's the maximum, because it points in the direction of steepest descent, the gradient, which points in the same direction, must therefore also point in the direction of steepest descent. So as I mentioned before, every function creates their own kind of landscape, and the loss function that we talked about earlier is no different. It also has a kind of landscape. And our goal is to reach the bottom of this landscape because the lowest point corresponds to the smallest error, and that's what we want to reach. And we initialized our thetas randomly. So for example, it could be that we start on our landscape somewhere right here, and all we have is the gradient of the loss function. But we know that the gradient points in the direction of steepest descent, so it points in this direction. But we don't want to go in this direction because if we did, the output of our loss function would become bigger. But that's not what we want. We want to go down here, so we have to move into the opposite direction. So in other words, we don't want to add our gradient to our current set of parameters because that would lead to a bigger output of the loss function. We instead want to subtract the gradient from our current set of parameters because then we move downwards and the output of the loss function becomes smaller. And hence the name gradient descent, because we're descending down here. We also don't want to take the full gradient step because that might lead to overshooting the minimum like this. So you could jump all the way over here and then miss the minima and then keep diverging. So you usually multiply it with a learning rate, which is a small number like 0.1, in order to not overshoot the minimum. So the update step is defined as your current set of parameters, theta, minus the learning rate times the gradient of your loss function, and this will give us a new set of parameters. And if we input this new set of parameters in our loss function, then the output of the loss function given the new set of parameters is smaller than what we had before. It's actually guaranteed to be smaller if your function is linear because the loss function is convex. And because our loss function is convex, there's only one minima out there, so there's only a single way we can move downwards. And so long as our learning rate is small enough, we are guaranteed to find the global minima as long as our model is linear. And there's also one more intuitive way to think about this, other than computing the Hessian and then proving that it's positive semi-definite. Imagine you had a data set like this, where it's not even obvious what the kind of trend is that you have out there. But for this data set, there's only one best line for the data that is better than all the other lines. For example, this line right here, it's perhaps not as good as this one, which in turn is not as good as this one. And it turns out that this line is the best descriptor for this data set, even though it's not a good one, but it's the best one out there. And because there's only one best line for this data, there's only one minima in our loss function. And all we have to do now is to calculate the gradient of the loss function. But luckily, we don't have to do that anymore by hand. We can just use automatic differentiation in one of those big machine learning libraries such as JAX, PyTorch, or TensorFlow, and they can compute the gradient of a function automatically. And in our next tutorial, we will implement all of this in Python and see how this gradient descent works in practice. So until then, thanks for watching, and I will see you in the next one.